During the past few years, my group has focused on the area of concentrated photovoltaics, a fancy term for converting sunlight into electricity in a new, ultra-efficient, and hopefully affordable fashion that opens new vistas within the realm of solar power conversion. The idea is to replace the expensive solar cells with affordable, clever, high-efficiency optics, which can be mass-produced accurately without any high technology facilities, unlike the solar cells, so that if we concentrate, let's say, 1,000 times, only 1/1000th of the system is the expensive solar cell. It shifts the burden onto the development of clever optics. Nevertheless, the cell is at the heart of this power conversion system. One of the systems we've developed is a rather novel optical system for concentrating sunlight to immense levels and then probing the complex solar cells that comprise the latest generation of ultra-efficient converters of sunlight into electricity. This is just a schematic diagram to illustrate how the multijunction or multi-layered cells that are now commercial can convert sunlight into electricity in a much more efficient fashion by exploiting more of the solar spectrum than any one layer can. This is a complex, expensive technology. The cells are quite expensive compared to the conventional solar cells with which you're familiar, like silicon, and that's why concentration is so critical. We have to reduce the fraction of the system comprised by this. This is just a photograph of the kind of system we've developed. We concentrate sunlight to enormous levels. This is a schematic of it. Couple it into an optical fiber, an optical channel to bring it inside a laboratory where we can work under controlled conditions. Here, we're interrogating cells. We're forcing them to reveal subtle physics under unusual conditions of very high intensity and very localized irradiation. This provides the kind of information manufacturers need. It informs them how can they improve the efficiency of the cells, how can they plan the next generations of cells. Here this is a 1 centimeter cell, here in a much smaller 2 millimeter cell. Incidentally, these are commercial, these are not laboratory curiosities, cells you can pick up a telephone and order. And they can be exposed to 1,000 times the ambient solar intensity. Here you just see circles we've drawn with different size fibers that we use to probe these cells. The major contributions I would like to hope we've made fall in two areas. One is in elucidating the subtle physics of complex ultra-efficient cells that enable us to now design future generations of more efficient and more affordable cells for solar power conversion. One. Two is inventing fundamentally new classes of optics, like here, for these cells, that can generate electricity at unprecedented efficiency and at prices that are far lower than conventional silicon-based photovoltaics, and they have been translated into the multi-megawatt systems now being installed. It goes from a desktop drawing, a fundamentally new idea in your head, and here it is in the field. So we have had the pleasure of seeing these stewarded into the field, and you see here from the tabletop 31 centimeter device to the module that's about 1.5 by 1 meters to a 9 kilowatt array, which now comprises the unit that produces massive electricity. In terms of miniaturization, again, the cells that can utilize the full solar spectrum, the trend over the last decade has been to transition from centimeter level technology to millimeter level technology. The motivation is multifold. These can be more efficient. They can be made with more precise microfabrication techniques that are now available thanks to the semiconductor industry. And their efficiency peaks at a higher concentration, a subtle point because it means that we can transfer more of the burden to the optics and make the system more affordable. They have a drawback. This is 1/100th the area of that. This is 100 square millimeters. This is just one. So the number of wires and contacts and peripherals increase also by a factor of 100. Fortunately, this is not a major factor, a major detraction, but it is something that has to be considered in the optimization. You see these metal grids, typically made of gold or other metals that can extract the electricity effectively from the bulk material to to the exterior. You can already see how manufacturers of 30 square millimeter cells or even 1 square millimeter cells are investing considerable efforts in determining non-uniform optimized fingers of these metal structures to more effectively extract the electrical current. The results of our research have informed this, and in fact we've even developed micro-optics. Optics at the level of 100 microns, micrometers and less, which can completely obviate the shading. It's a parasitic loss. All the light that strikes those grids are reflected out, and you're paying dearly for those photons, for that light. We can now design optics which can redirect even concentrated light and put it right where it belongs rather than where it would have gone otherwise. Just as an aside, let me mention we've also demonstrated the fact that these cells can be cooled in a totally passive fashion. It's proven you don't need forced circulation hydraulic systems with all the parasitic requirements, with all the complications, and it's a fail-safe mechanism. The cell resides on a simple aluminum plate, which in any event provides the casing, the enclosure for these modules. This is a sol focus array that generates 7 kilowatts. It comprises a large part of their current installations in Europe. This is the 1 centimeter technology. So yes, first we perform the laboratory experiments, do the thermal physics, prove it with experiments. Now with confidence we can move to megawatt systems, and indeed these are being monitored and they are performing only 20 degrees centigrade above the environment, which poses no problem. It's even better for the millimeter technology, but this is not quite ready for prime time. This is still in the R&D stage. Another area in which we made contributions is understanding how can you design high-performance optics tailored to these particular types of cells. The ordinary Fresnel lenses you'll read about on the internet and you can buy off the shelf suffice for intermediate to mediocre performance. But if you want to obtain the most out of these, and because cost is a relevant factor in addition to the physics, you must have maximum performance optics. These are 2 generations of optics we developed for the Sol Focus Corporation of California. This one for the 1 centimeter technology. This comprises the workhorse of their technology today, and I'll show you some examples of multi-megawatt systems now being installed. In addition, what's on the agenda, what's in prototype development, research and development, is for the millimeter technology cell and for a new kind of micro-optics made of all glass. Areas of solar research in photovoltaic power conversion of major potential impact. Where will the breakthroughs come during the coming decade or 2? I'd like to divide it into 3 basic categories: materials, optics, and nanofabrication. In terms of materials, this is a state-of-the-art schematic of a state-of-the-art solar cell which uses 3 different materials. This is just a graph of how the intensity of the sunlight we receive on Earth depends on the wavelength of that light. And it's just illustrating how each of these materials is tailored to a part of the spectrum. This is state-of-the-art today. However, by using more junctions that are better suited to the solar spectrum, the potential for improving conversion efficiency is prodigious, meaning as much as 50% relative. This is enormous in technological terms. So one direction is, what are the materials? How do we identify them? How can we fabricate them? And how can we assemble cells like that? How can we take better advantage of the spectrum that nature is granting us? The third one, which I don't have a slide for, is in nanofabrication and microfabrication. If these new semiconductor processes, if these semiconductor layers, if the optics are going to be miniaturized to the millimeter and sub-millimeter level, then micro and nanofabrication techniques that are accurate, affordable, and reproducible on an immense scale must be developed. There has been enormous progress. We're at it. The technology is really in its infancy, and the amalgamation, the fusion of these 3, of materials, optics, and nanofabrication, I think are going to give rise to a new generation of a complete package of optics, photovoltaics, based on new material science. This is what I find exciting. Second one is in optics. This is just one example of a fundamentally new class of optics, in this case we developed. This has been adopted by Sole Focus, where many questions are asked in terms of, can it be maximum performance in terms of how much light is delivered at a very high intensity? Can it be delivered efficiently? Can the system be ultra compact rather than deep? That's a major factor in the price of the system. Can it be made from existing manufacturing processes and existing materials? So this is, let's say, where we stand today. The potential for improving this is also not small in terms of relaxing optical tolerances, meaning the systems can be made much less expensively. Can the throughput, the optical throughput, the amount of energy that's lost because of unwanted reflections or absorption, new coatings, that's also part of the challenge in optics. This is another example of the 1 centimeter cell optics that we've developed for Sole Focus, which is all glass optics. All glass optics for centimeter technology is ludicrous because it weighs a ton. The moment you reduce it by literally a factor of 10, it becomes comparable to a pane of glass. Now we can talk about microfabrication techniques with clever optics, and this is just where we stand today. There is improvement, and we know that from fundamental laws of optics. So yes, there is a considerable room in optics and optical materials.